Number 10 on 1.4. Okay, so number 10 asks for the equation of the tangent line. So anytime we are going to write an equation of a tangent line, we think of this, right? And I think you were supposed to look back at the graphs at the beginning of the section, right? And it wanted to know when t, or x in this case, 6.5. So what we need is a point, and they wanted it on the p graph. So we need the point at 6.5, and we need the slope at 6.5, correct? Now, so you go to the p graph there, right, on page, whatever that page is, and you look at 6.5, and what's the y value there? You have to kind of estimate, don't you? Negative 45, okay? Sounds about right. Okay? So, and on a situation like this, if this was on our next quiz, you know, you would have some leeway. Maybe you thought it was negative 40. Now, does that make sense? Are you seeing that? Okay? Negative 40, negative 45, you'd have a little leeway. All right, and then we want the slope. Now, you would have, it depends on the information you were given. In this particular problem, I believe we were given the p prime graph, weren't we? Isn't the p prime graph the one on the right, the velocity graph? So the best thing to do would be to read off of it then, its output. Right? Now what if we weren't given that v graph there, though? How would we find p prime? Draw a tangent line. So you would want to go in to the graph at 6.5, and it might be right down here somewhere, and you would draw yourself a tangent line like so, and then you would do kind of a slope triangle thing, do a rise and run, right? And to estimate that slope. All right, but since they gave us the p prime graph, I would say let's just read right off of there at 6.5. And what do you see? Negative how much? 60? Shelby, what do you think? Since you asked, negative how much? 58? Sounds good. Okay? Yeah, there's a big gap there, right? I mean, so who knows? So that'll be fine. So now that's our slope. Here's our point. So we simply go y equals negative 58 parentheses x minus 6.5 plus negative 45. I guess I could have put minus. That's it. Right? Find the equation of the tangent line to the p graph at 6.5. So we need the point and we need the slope. The point on the p graph is p of 6.5. The slope on the p graph is p prime of 6.5. That's it. What else? Same section? That's the speed limit law stuff, right? It says that f of 0 is equal to 2. It says that f prime is what? Greater than or equal to 4. That means what? Who asked about this one? Spencer. What's f prime greater than or equal to 4 mean?
It means that it can only be, it can be like 5, 6, 7, 8, but it can be 3, 2.
And when you say it, you mean what?
Yeah.
Since it's f prime represents slope, right? So the slope. The slope can be 4, 5, 6. So if we go over 1, we got to go up 4. Go up over 1, go up 5, or whatever. Okay. And what do they ask us about?
What can be said about the values of f1 and f-3?
Okay. So first we'll do 1. So f of 0 is 2. So here we are right here. So if we go over 1, we got to go up at least 4, right? Now we're already at 2. So that means we might go up as high as 6 or more. So f of 1 has got to be greater than or equal to 6. What about negative 3? If we go back 1, 2, 3, that would be a run of 3. We'd have to go And wait a minute, if we go back, we have to go down 12. So if we go down 12, that would take us down to what? Negative 10? And we could have went down more, right? So it's going to be, so f of negative 3 would have to be less than or equal to negative 10. Make sense? Because we could have went back 3 and down 15, right? If the slope would have been 5. So we might have went farther back. Okay? Because our line, if we're going to have a slope of 4, right, this would be our line. So it's got, that's why we have to go down. All right. Anything else in section 4? What about 54? Is there anything bothered anybody about that one? Let me, without actually working them out, but explaining what you could do there. This is that height equation business. Here's the height of a ball that's thrown up, or an object that's thrown up, or dropped, and affected only by gravity. So these equations ignore wind resistance and those kind of things, right? And then velocity. Now the velocity could also be called what? H prime, right? The velocity is the same as H prime, and that equation is v sub 0 minus 32t. Those were given to you, and I wrote those up on the board yesterday, and those are, whoops, in the example. All right, now, let's go. All right, so we've got this. So let's just talk through this. On A, it says, from what height was the ball thrown? Well, that's what this is right here. So in that problem, it was 74 feet. Okay? B, what was the initial velocity? That's this number right here. What was that? 38. Was it thrown up or down? Up. How can you tell? The 38 is positive. If 38 is positive, it's thrown up. If it's negative, it's thrown down. Okay? C, was the height increasing or decreasing? Means was the ball going up or going down at 2? What would we do to tell? Okay, one thing you could do is graph it. But let's say we were not using a calculator. You could graph the H equation and trace it to and see if it's going up or down. But let's pretend that we didn't have a calculator. What else could I do? Yes. Here's the key. Plug it into the velocity. It relates to what we just said. The 38, we just said the ball was thrown up because the 38 was positive. The velocity was positive. Plug 2 into the velocity graph and see what you get. And if you get a positive, it's going up, and if you get a negative, it's going down, right? Plugging a 2 into the height graph doesn't do anything for you. It just tells you how high it was. It could have been on its way up or on its way down. We don't know. Plug it into the velocity graph. You put a 2 in the velocity graph, it'll tell you if it's going up or down. Okay? D. When did the ball reach its maximum height? And this really connects with what we're going to be talking about today. Without graphing it, what special thing happens to this graph when it gets to its height? This is the height graph. When it gets to its max height, what special thing happens? Slope is 0. Right. That's going to be a big deal for us today. The slope is 0. Which one of these equations is the slope? The velocity graph. So what could we do? Set, not plug in, but set it equal to 0. Several of you did say that. Set the velocity graph equal to 0 and solve it for t. That'll give you what? The time that it's at its peak. Is that what they wanted? Yes. At what time did it hit its maximum height? That's what they wanted. How high was it? So what would you do with that then? Plug that t value into the first equation, and that'll tell you how high the ball was when it was at its peak. Last one, how long was the ball in the air? What do you do for that one? It was thrown at 74 feet, it goes up and it comes down. Isn't that what you want right there? Set what? Set the height equation equal to 0. Set the height equation equal to 0 because that's when its height is 0 is when it's back on the ground. And when it's back on the ground is the time then, that's how long it was in the air. Okay? It was in the air that whole time until the height is 0. So you take the height equation, set equal 0, and solve that. And which you could solve just on your calculator. Okay? You can just do a solve thing there. We'll do more of that later, so I'm not going to take time to do that. Okay? But there you go. So that's just an example of using an equation and where we can use the velocity or the derivative equation to tell us some information about what's going on. Okay? All right. What about 1.5? Pretty short one, really, and judging from what most of you had, it looked like you were. I mean, here's the thing. From 1.5, and we did get a chance to talk through all of that yesterday, the big deal on this section is just being able to do a slope calculation. As we get done with section 4 and 5, the main things you get from this is 4 is about the derivative. Section 4 is just when we first told you that derivative means slope, and slope of the tangent line and all that stuff, right? I mean, just the concept. So 4 is really a big section on just concept of the derivative, rate of change. All right. 5 is then about kind of making some calculations. The two calculations we want to be able to make are this. If we have a curve, we want to be able to take a tangent line like so, and we want to be able to do like a slope triangle, rise over run. Just a simple little estimate of what a slope is. Okay? And then the other thing we want to do is be able to actually do a slope calculation using some actual points that are really close together, and that's this idea of zooming. So let me take a second to just do number 14. And I think maybe we even talked about this one a little bit. But if I would graph, so on 14, you're supposed to do sine x, okay? And I think I even showed you this. Did I show you the thing about tracing and hit enter twice? So trace, so we want to trace at 3, hit enter twice. It gives me this point, and now I wanted to zoom in. They wanted me to zoom in at this point. So I'm going to zoom in. Looks like I got a negative slope there. I'll zoom in till it looks straight. Now, the actual act of zooming in, that's not going to be on the next quiz. I mean, where you physically, I'm not going to ask you to give me a window, zoom in, okay? But I wanted you to go through that process and do this because I want you to really see the concept we're after here is that when we draw a tangent line, if we zoom way in, the line and the curve around that point are basically the same. Even though the line only touches the curve at that one point, they're basically the same. So if we would take 2 points on that curve, it's just like taking 2 points on the line. But for the actual calculation, I'm just fine if you do this. Instead of trace and write down the points by hand, I'm perfectly fine if you go to your calculator screen and do this. Sine of 3.001 minus sine of 3, and then all of that divided by 0.001. Right? Isn't that a slope calculation right there? It's the subtracting the y's at 3, subtracting the x's, 3.001, take away 3, and then hitting enter, writing that on your paper, right? And that is that f of b minus f of a over b minus a. It's just a simple slope calculation. Look what we get, almost -1, which seems reasonable. At that point that the slope is about -1, right? So I want you to understand that concept of taking some f values close together, doing a slope, that's an estimate of your f prime. That's the basic idea in section 1.5. So not a whole lot going on there. All right, let's. We got a lot to get to today, so let's go ahead and get started with this. I sent you 2 documents. Did everybody get it? It only says we got 20 people logged in. How many we missing? 3? We should have 21. Did everybody get these? Okay. We got 2 different ones. Derivative grapher and first derivative test. The first one we want to do is derivative graphing. Okay? Now this one you're just going to kind of follow along with me here. The first derivative test is actually an activity we're going to do in a worksheet you're going to work on here in a little bit. Okay, so you got to make sure you have that. We had a little trouble with this, not sending some stuff for second block, so I restarted everything, so I'm hoping it's working. All right, so if you want to get your notes out, there might be a few things you jot down. I don't know. I told you that as we go through this next week or so, there's going to be some head spinning, some trying to keep track of all these different things, and that's okay. I mean, I'm kind of purposely not overly organizing the stuff that we talk about right now, because I want you to just have to think your way through it and not just memorize a list of steps, okay? Because I just don't think that's the way to get the concept. Now, as we go along, by Tuesday, we will be starting to put this together in kind of an organized form where we can kind of keep track of it. And then we will kind of memorize it. But we will memorize it in a way that we get the concept, right? And that's how we memorize it. So, so here we have, I showed this the other day. So the red graph is F, and the bottom graph is F prime, which means the bottom graph Y values are what? Slopes of the red graph, right? So when I talk about the blue graph, what I'm saying, and I say, what's the blue graph? I'm asking for the Y value, is what I'm asking about. What's happening to the Y value, the output. Okay, so let's pretend we can't even see the red graph right now. Okay? And we're going to just focus on the blue graph. Because one of the things that you will do over the next several days is I'll give you an F prime graph and ask you questions about F. Even give you an F prime graph and ask you to draw what the F graph would look like. Okay? So that's what we want to think through right now. So let's start right here. So let's focus on this point right here on the blue graph. What could you tell me about that point? Right now. Where it is. And let's just focus on the Y value. So, Aaron, positive. That would be the first, that would be one of the things I would want you to say. If I ask you about that dot on the blue graph where it is right now, that you'd say, hey, it's positive, right? Because it's above the x-axis. Now, let's think about that. Those Y values are the slopes of F, right? So, if it's positive, what's that mean about F? Going up. Increasing. So F is increasing, right, at this point. Okay, what else can you tell me as I move this black dot? What could you tell me about the blue graph? Okay, it's decreasing, which another way to say that is getting less positive, right? I would agree with that. So the blue graph, as I move that dot, it's still positive, so the red graph's still what? Increasing. The red graph's still increasing. We can peek at the red graph, and sure enough, it's increasing. But what significance does it have that the blue graph is positive and getting less positive? What significance does that have to the red graph? What's the term? The slope's getting closer to zero. The slopes are positive but getting less positive. What do we call that? I wonder if the people watching the video can see what I'm doing right now. The slopes are positive and getting less positive. Yeah, they're approaching zero, but what do we call this curvature? Concave down. Isn't that the significance? Now, let me back up just a second here. If I was to summarize what we're trying to do in this section, all the stuff that we're going to be working on, it's this right here. What does F prime tell me about F? I mean, that is what we're working on right here. What does F prime tell me about F? Now, right now, it seems I got two things. In this little exercise so far, it seems I got two things. it seems that when f prime is positive, tells me f is increasing, because f prime is slopes, and if slopes are positive, that means they're going up, the graph's going up. And it also seems like when f prime is positive and getting less positive, that decreasing, it seemed to be concave down. F seemed to be concave down, right? Let's keep going, see what else we got. So we keep going, and we're looking at the blue graph now, and so we're still positive, getting less positive. And then all of a sudden the blue graph does what? The blue graph is, now remember, I mean the y value when I say this, right? The blue graph is 0, right? 0. The y value right now is 0. Okay, yeah, that's not a hole in you. You're looking at that hole. Yeah, don't worry, that's not a hole. That's just something I can grab. So that white thing. So right now it is, 0. So the blue graph is 0. Whoa, slope is 0. What's that mean on the red graph? Now, I heard local max. I heard the word local max. Yes. Now, just because the slope is 0 means horizontal, right? So let's do this, because it wouldn't have to be a local max. It could be local min. It could be several different things, which we're going to talk about in a minute. So let's just call it a flat area right now, right? When the slope is 0, the f graph has to get flat, right? Because that's what slope 0 means. Okay? So when the blue graph, when the slope graph, when f prime is 0, the f graph has to get flat. Let's just say that for right now. Okay, let's keep going. Now what's f prime? Negative. So f has to be decreasing, right? If f prime is negative, the slopes are negative, then the graph's got to be going down. But the blue graph is negative and getting more negative, which is still decreasing. See how there's two different ways a graph can decrease? It can be positive and getting less positive, or it can be negative and getting more negative. Now let's talk about that in terms of slopes. So let's go back to this picture. So here I had slopes that were positive and getting less positive, and now I got slopes that are negative and getting more negative. What's that mean? Still concave down, right? It still means concave down. So the graph, so positive slopes getting less positive and negative slopes getting more negative seems to mean concave down. So it seems like we were on the right track. It seems like when f prime is decreasing, doesn't matter if it's decreasing as a positive or decreasing negative, it seems to mean the f graph is concave down now. So there seems to be a connection there. Okay, so we keep going, and pretty soon the slope graph gets to a bottom. It's negative, but it's not getting more negative anymore, right? It's about to start getting less negative, so what do we call this? The max slope, or the steepest negative slope we're going to have. What do I got on f now? We're at an inflection point, aren't we? Okay, so there seems to be a connection there between something on f prime telling us something about f right there. Okay, let's keep going. And now we're negative. Blue graph is negative and getting less negative. The blue graph's actually increasing now. So what is negative? So the red graph has to be what? Since we're still negative, the f graph is going down. So the f graph's still going down. If we peek up here, sure enough, the f graph's still going down because this graph's still negative. But now we're getting less negative. So if we go picture that, what's a negative slope that's getting less negative? Oh, I gave up. Imagine that. All right, yeah. Wow, surprise, surprise. All right. So we keep going, and pretty soon the slope is 0, right? The slope is 0. The blue graph 0, so the f graph is a flat area again. Okay, and then we get to now the blue graph is positive y values and getting more positive. And what would that be? Slopes that are positive and getting more positive. Oh, that's concave up. So negative and getting less negative, or positive and getting more positive. That's an increasing situation. So here, when the blue graph, when the slopes are increasing, that seemed to be when this was concave up. And then once these slopes went positive above the x-axis, this graph seemed to start going up. Okay, so if you look in your books on page 55, there's a picture there very much like this, almost identical to this scenario here that we just went through. So if we raise the question, what does F prime tell us about F? Seems to be there's quite a bit, right? There's quite a bit about the blue graph we could investigate, and there would be some corresponding thing that's happening to the F graph. So there seems to be this connection. So we're going to be putting that together over the course of a few days here. Now, let's see. Next, well, let's just go. Let's jot down a couple of definitions here. So let's investigate this idea of a flat area. Okay, that seems to be kind of an important deal where we have that local max and that local min. When the slope is 0. Now, when if you're looking at an F prime graph, when are its y values 0 on a graph? Crosses the x-axis, right, like the x-intercept. So that seems to be a pretty important deal right there. If we have an F prime graph, we might want to zero in. Pardon zero in on the x-intercepts, all right? We might want to pay particular attention to those points. That actually has a name here. Those are called stationary points. Stationary points. Now, okay, stationary point. We'll write the definition of that. Now, x equals a is a stationary point. So in other words, it's the x coordinate we're talking about, right? When we talk about stationary point, we're talking about the x value. X equals a is a stationary point of f of x if f prime of a equals 0. Okay? If the slope at that point is 0. So that would mean the output on the F prime graph is at the x-axis, right? Is 0. Now the word stationary point, let's put this in instead of slope, let's talk about velocity here a little bit. We said slope derivative could also mean rate. So let's talk about that Bismarck, North Dakota. So if I'm driving and I'm going east, the velocity is positive, right? So that's a derivative. So the derivative would be positive if I'm going this way. If I turn around, the velocity is negative. And so at the instant when I turn around, the velocity is 0. I'm stopped, right? When the velocity is 0, I'm stopped. So the word stationary kind of makes sense from that standpoint, right? Stationary points. It's kind of like when it stops going one direction and starts going another direction, right? Now it's possible that I could be going east, stop, and then keep going east, right? So I wouldn't have to change direction to be a stationary point, okay? But when the derivative is 0, the rate of change is 0. Yes, now, okay, that gets into one-dimensional versus two-dimensional. So if I'm going east and I make like a U-turn, that kind of thing, okay? So if I make a U-turn like this, and I never really stop moving, but remember, we defined the velocity to be eastward velocity. So when I do this, and I make this U-turn, there's still a point right in the middle of that U where my eastward velocity is stopped. My eastward movement is stopped, and now I'm going north-south, right? So yes, because then you get into two-dimensional kind of thing, east-west and north-south. Then you got bigger problems, right? I mean, which we will actually deal with some of that when we get into later. But for right now, yeah, that's why we're so careful to say eastward velocity, or we were talking about just vertical velocity, like the balloon going up and down. Okay, so if the balloon actually does this, it never really stops. At some point, it stopped going up. So its vertical velocity did stop. Okay, so let's talk about that as it related. You guys were using the term local max, local min, and that's all good. If you look on page 55 there, you can see there's tons of bold-faced words. Well, we've used most of them already. Local max, local min, inflection points, concave up, concave down, all that stuff. So let's look at, there's really three possibilities where a function can have a 0 slope. One possibility is a local max. Okay? Flat area. derivative is 0. Okay? One possibility is a local minimum. Okay? Now these would be F graphs that I'm drawing here, right? I'm drawing F graphs, and I'm drawing them where their slope is 0. Okay? But the other possibility would be this, where it comes up and does that. Where just momentarily it's flat, the slope is 0, but then it keeps going the other way. And that would be kind of like this situation where I'm driving east, I slow down, I stop, and then I start up again, going the same direction. So you don't really have a local max or local min, you have what we call a flat spot. I don't know what the technical name is, that's just what I call it. I think I heard it in a book, I think someone said a terrace point or something like that. But I don't, you know, that could be called, but typically we'll just say a flat spot. Okay? So those are the three different, there are no other possibilities. I mean, think about a graph. Is there any place it could flatten out and do anything different? I mean, now you could get a line, I mean, you could get a piecewise or something that just was a line for a while, and then it's just one big flat spot. And it's just flat on the top. That's a constant slope. But otherwise, these would be the situations. Now, you can get graphs that have local max and mins, have multiple local max and mins, right? This is a local max, this is a local max, this is a local min, here'd be another local min. Okay, one of those maxes is higher than the other, it doesn't matter, they're both, so local max min is like peaks and valleys. Now there is a term that they are going to use in the book that they're going to ask you about, global max. Let's just talk about this real quick. Global max min. Now this isn't really a key thing for us here yet. I think there is one homework question that might mention this, but we won't get into this a great deal right now. Global max min is the highest or lowest point in the interval. Okay? It's possible that you don't have a global max or min. I mean, for example, if you took x cubed, which just goes off in both directions forever and ever, there's no highest point, no lowest point. Now, if you were going to talk about a closed interval, if you were only going to look at x cubed from, say, here to here, you know, then you might have a highest or lowest point. And it might not be the same as the local max min. Let me give you just a couple quick little pictures here. Let's say we were looking in a closed interval right here, and we had this graph that did this. Okay? Now, where's the lowest point? Right there. So the global minimum could be at an edge. This is where the slope isn't even 0, right? So it might not have anything to do with the slope being 0. It might be at an edge. The highest point is here. Now, that's also a local max. This and this are both local max. This happens to also be the global max. Does that make sense? Okay. So a global max could be at a local max, but it could just be at an endpoint. Just like the global min could be at a local min, or it could just be at an endpoint. So local mins and maxes are like peaks and valleys. All right. Global max and mins could be at local max and mins, but global max mins are just the highest point or the lowest point. Okay, our focus really right now is more on this local max min kind of idea. All right, now we're very interested in those. I mean, if we had a profit equation, we might want to know where the max profit was. If we were trying to get out of a snowmobile jam and go to the gas station, right, we might want to know the minimum time. That one's probably not as realistic, but right, we might want to know a minimum. So we might be interested in these max and mins. So where are we going to look? We're going to look where the derivative is 0. Right? Because that's where they're going to happen. So the derivative is a big deal for us. All right, let's got one more definition here, and then we're going to do this calculator activity. All right, critical point. Critical point. This is kind of like a square and a rectangle. Okay? A square is a rectangle. A square is just a special kind of rectangle, right? Well, same thing here. A stationary point is a critical point. It's just a special kind of critical point, right? So x equals a is a critical point, I'm just going to abbreviate that, of f of x if f prime of a equals 0 or f prime of a is undefined. Okay? So if f prime of a is 0, it's a critical point. It's also a stationary point, because that was a definition of stationary point. Or f prime could be undefined. Then it's just a critical point. So somebody was asking me in their class if this was true, and that is very true. All stationary points are critical points. Right? That is a true statement. All stationary points are also critical points. So if we have one and you call it a stationary point or a critical point, either one of those you will be correct, right? But if I showed you a picture of a square, you would almost all say that's a square. You wouldn't say that's a rectangle. You'd be right if you said that's a rectangle, but usually call it a square, right? So if we have something where the derivative is 0, we usually call it a stationary point, even though you could say it's a critical point. That would be true. All right, so let's look. There's 5 different possibilities I want you to consider here. So there's 3 of them that we just wrote on the other page if the derivative is 0. If the derivative is 0, you could have a local max, you could have a local min, or you could have a flat spot. Oops. That's not a very good picture, but anyway, you get the idea. Okay, local max, local min, flat spot. So you got 3 possibilities where the derivative is 0. And then if the derivative is undefined, this was the thing that I came running back in to show you yesterday, right? That I thought of on my way out the door. Sharp points. Like you could get a graph that does something like that, like a V graph, or it could have curves to it too. Okay, but if you have a sudden change in direction, okay, the slope where there's a sharp point, but look, that's a local max, right? So you could have a local max at a place where the derivative doesn't exist. Okay, so you're going to discuss that a little bit in your activity here. And then the other one, if you remember, was a vertical tangent. So if you get a graph that does something like this, and it's got a vertical tangent, the slope is undefined there as well. Now that's not a local maximum there. It's not written, it's not a flat spot. It's just a vertical tangent. Here we have a horizontal tangent, so the slope is 0. Here we have vertical tangent, slope's undefined. So there's 5 different possibilities for critical points. Okay? These 3 are stationary points when the derivative is 0, and those 2 are when the derivative is undefined. But all 5 of these are critical points. All right. So you're going to do an activity here, a worksheet, but if we call it activity, it sounds more fun. Worksheet. And you can work with a partner or 3. And you're going to fill this out, and then there's a short book assignment after that. But we're going to want to kind of wrap it up together when as we get done with the worksheet. And if it works, I'm going to at some point in time I'm going to shoot you a question or 2 to have the answer on your calculator. Okay. Now, so you need the first derivative test document up. Okay, the first derivative test document's the one you want to have up, and the first top half here of the worksheet just gives you the definition we just wrote. It tells you what a critical point is, so you can pass by that. And then it gives you another definition about what a local max and local min is, and basically it's just what I told you. It's just the peak in the valley, right? It's the biggest point in a small region. So you can go right on to where it says move to page 1.2. Okay? Now, I want to help you get started a little bit here, and then you can kind of go into your group. So let's go ahead and look at the document. First derivative test. Okay, it says each page in the document has a graph of a function with a single critical point. Grab the white point on the x-axis and move it to see the slope of the tangent line change as you move along the graph. So how do you grab that white point? You can do this. I think you can click and hold. Somebody was telling me you can hit Control and then hit the middle of the trackpad, and that will close the fist and then let you move it. That's a pretty good way to do it too. So everybody see if you can do that, and so you can click and drag this thing. Okay? All right. Now we're going to complete the table. Now I'm going to let you go ahead and get together here with some people to finish this, but I want to make sure you understand what the column headings mean. So the first one, it says critical point and reason why it's a critical point. So what are you going to write in there? X equals what? Right there. We're on the, yeah. Oh, okay. Right? So x equals 3. And then the reason, why is that a critical point? Because f prime of x equals 0. You can just write f prime. You don't have to put the x's. Okay. Because f prime equals 0. There's only two reasons why something's a critical point. Either f prime is 0 or f prime is undefined. Right? So at this point, f prime is 0. Okay, so you put that in that same box. Okay, what's that second box mean? The next column, location of local max, local min, or neither. Wait, they didn't word that very well, I don't think.
Is the critical point a local max?
Yes, Alex, say that again.
Is the critical point a local max or minimum?
Yeah, what they're asking is that critical point you're looking at, is that location a local max, a local min, or neither? So what are you going to put in there? So you're going to write in there local min is what you're going to write in there. Okay? The next column says interval where the slope of the tangent line is positive. From 3 to infinity. The tangent lines would be positive from 3 to infinity. So you'd put our interval notation, 3 comma infinity, right? And close it. Now, no, they'd be open brackets because the slope is not positive at 3. We'll be doing a lot of interval notation in these next coming days. Whenever we're talking about where is a graph increasing, decreasing, concave down, concave up, all that stuff, never close the parentheses. You'll never go wrong, I don't think, on these if you just leave them as open parentheses. Okay? And then where's the tangent line negative? Negative infinity to 3. Yeah, we can assume it just goes up to infinity. Okay, so if you want to get together in some groups now and finish that front side and then go ahead and do the back side, you are certainly encouraged to do so.
Thank you for making this all like 2. Yep. Nice numbers.
And you'll notice that when you get to like sharp points and stuff like that, that it does not, it shows you that there's no slope, I think. I think it's supposed to. That's kind of cool. Let's see where you guys are. Yes. Right. If it's never negative, yeah, I just put never. You know, if it's never negative, just say never. Yeah. None, you know. Now the part where now and this is critical on the part down at the bottom of the page it says summarize your findings. Now don't skip over that where it says summarize your findings. I want you to think of this now. Look at the last two columns. Look at the last two columns and see what bearing those had on whether you had a local min or local max or neither. That's the findings that we want to focus on. Yeah, this is kind of tough. Do I want to, because I'm going to interject some stuff. But